Hi, I'm Josh Pennell with IOActive, and this is Mike Davis, and we're going to talk a little bit about some of the hypervisor research that we've done recently. Basically, the way that we've approached this certain subject is that if you're sitting in your organization and your management team comes to you and says, hey, we're looking into deploying our infrastructure into the cloud, or we're looking to develop an internal private cloud for the organization, some of the things that you probably want to think about and from a security perspective. So this is particularly applies to IaaS. All right. So a little bit about us. Won't belabor this too much. We've been around since '98. One of the things that is kind of important for this talk, I suppose, is that we're one of the few firms that actually have looked at all three major cloud computing platforms. Some of the major companies that are close and dear to your heart. We've reviewed their systems. High-end software and hardware review company, been around for a bit. So here is our agenda for today. We're going to go over the history of the hypervisor. For those that don't know, raise your hand if this gets boring, but we find it kind of fascinating because, of course, it's kind of revisiting the past to determine what's going to happen in the future. We're going to go over the architecture of hypervisors and why you should care from a deployment perspective, the attack surface of the hypervisor, some of the attacks that are known now, and some of the attacks that might happen in the future. And then some of the summary of what we've talked about with some remediation paths forward. So there's the hypervisor history. For a lot of you probably understand, but hypervisors are certainly not new. Stemming clear back to 1960, we've got the IBM M44 that's fired up. Mainframe application. It had para-virtualization, so it wasn't complete full hardware virtualization yet. It was a hybrid. And then in 1961, they found that the CTSS system needed to have a backwards compat capability for the 7094 for Fortran. And then moving on from that, those are, Robert Creasy didn't really think that these systems are true virtualization systems, and then he moved on to do the IBM S360, which was a full-on hardware virtual machine, which he called the pseudo machine. So we thought this was kind of interesting that we're certainly not we're not breaking new ground here or anything interesting like that with the new x86 architecture. So moving on from there, there's the IBM 370, which kind of formalized more of the 360 concepts and brought a lot of the newer technology to the market. And then the Popek and Goldberg paper kind of set the rules about what a hypervisor needs to do and what it needs to act like.
Is anybody actually familiar with the Popek and Goldberg paper at all? Are you familiar? Okay, so we have one person. A couple of people, okay.
Yeah, so we'll talk a little bit about what the rules and the constraints of what a proper virtual machine would actually do in the next slide. Moving on from there, some of the x86 architecture proper didn't really enable virtualization to occur, unlike the mainframe days where you actually had physically separated LPAR systems that would allow for fully virtualized S360 systems. So they needed to do a little bit of work. And one of the major technological innovations at that point was the introduction of rings in the Intel 286 chip, which was kind of a step forward where people were starting to go, maybe we're going to be able to use this new x86 architecture to be able to introduce a hypervisor-like system.
What's also sort of interesting about this sort of point in history is it's kind of where deep research into virtualizing other systems sort of fell off into sort of commodity hardware. This is where we started seeing sort of cheaper attempts to approach virtualization on 286-based systems rather than having an IBM mainframe hiding somewhere in your business. But what's really interesting is right after this is there's this huge gap where virtualization just didn't seem to be important to anybody.
10 years or something.
Yeah, 10 years or 15 years, something like that. And eventually it seems to pop up again, and I think only really around 2006, which is what we're coming up on here, is where we started talking about actual hardware-based virtualization again.
Right. Yeah, so you've got a major gap from about 1986 to 1999 where we weren't able to identify a lot of virtualization technologies that were out and about. So in 1986, you probably all remember the 386 or the i386 chip came out. It actually had a virtual machine in it that emulated the 8088, 8086, the 108088, something like that. And they did that for backwards compatibility for the DOS virtual machines. So
this was also sort of the beginning of where we were getting to the point where we could have process isolations and process private address spaces. And essentially, each process got to act as though it were in its own virtual machine. And that's sort of the beginning of this, but 286 wasn't quite good enough.
So then some guys at Stanford took the step into the deep end of the pool, and in 1999 they decided to bring virtualization back to the x86, and they did some very, very complicated software programming techniques with binary translation, on-the-fly dynamic compilation of trapping processor codes and emulating those back into the hypervisor and the virtual OS. So they did a lot of heavy lifting. I'm pretty sure they used every programming language known to man to develop VMware Workstation, which was their first release in 1999. They were founded in 1998, so you can see that they really took the product to market fairly quickly. Shortly thereafter, Microsoft's close on their heels with the virtual PC release, and then VMware ESX Server, which was one of the earlier bare metal hypervisors, was released in January 2001 approximately.
Yep. And keep in mind, like as you're getting to these initial hypervisors, these are all sort of dealing with the crippling nature of the x86 as a platform. There's a number of instructions which are considered sensitive instructions, and if the guest system were to run any of these instructions, the host system could potentially lose control. And that's where we started seeing these really bizarre methods of dynamic patching and, basically trying to predict what the virtual machine was going to do so that they could patch instructions to make that happen. And this had a whole bunch of problems, and you can actually, well, I think we have a bunch of the sort of vulnerabilities later on talking about those. And then we started realizing that these are real problems. The x86 as a platform has to do something fundamentally different before somebody can actually use it for virtualization in some sort of a security framework.
Whereas back in the mainframe days, these systems were geared to do this. So it's interesting.
Yeah, actually, just to sort of jump back to the IBM-based systems. I mean, when they engineered the original IBM ZOS ZVM systems, essentially they understood that these multiple users are potentially working on military data, private data, credit card information. So it was very important to them that they could have many of these virtual machine systems, but they needed to make sure that none of these systems could actually talk to each other, interfere with each other. So that actually went into the hardware layer of things. And interesting, if you look at our plot here, the Popik and Goldberg paper actually came out after the S370, S360 systems, which were actually fully Popik and Goldberg compliant. That was a system fully capable of implementing LPARs in such a way that even covert channels, cache timing attacks, and things like that weren't even possible. And now we're sort of getting into the end of things where we're talking about x86-based systems, and covert channels, resource starvation, things like that suddenly became problems. If anybody's run VMware Server back in the old days and you had multiple VMs going, and I watched this happen with many CTF games, the CTF game ultimately goes downhill because one team spins up a fork bomb and every other VM just crawls to a halt.
Right.
But
so you can see, like, moving on here, we've got this new class of processor that came out for the x86. That you have AMD Pacifica technologies and the Intel Legrand technology. And this was basically taking some lessons learned back from the mainframe days and making those codes available within the x86 architecture to prevent things like blue pill and whatnot. So again, we got the classic arms race. Research comes out, hardware vendor responds, or software vendor responds with new feature set.
So everybody knows Ring 0. You're familiar with Ring 0. So once we realized Ring 0 wasn't really good enough to handle the virtualization problem, we introduced Ring -1, and feel free to try Googling for that one of these days. It's a basically impossible Google term. Ring -1 was essentially the somewhat ugly fix to a lot of the virtualization problems. They pushed the OS down and said, okay, you can have Ring 0, but we have to have a hypervisor that runs under Ring -1. And in this case, many of those sensitive instructions are now separated from the actual Ring -1 architecture.
So here's the litmus test that most VMs are compared by. Again, so when you're looking at technologies or the approach that you're going to use in your organization to roll out your private cloud, or in the UK they call it the G Cloud, where the government's consolidating about 180 data centers into 6, called the G Cloud. Sounds really exciting. This kind of some of the things you probably want to ask yourself, particularly the second point here, resource control and safety. Will your hypervisor actually prevent proxy out the ask for actual physical hardware resources? That's the real #1 question. Because if you look and dig deep into the design of these systems, you'll see that there's occasionally you'll see an interesting thing where it bypasses the hypervisor from the guest OS to the hardware. So you want to go like, that might not be compliant. Maybe not the right hypervisor I want to use in my environment. Okay. So here's the hypervisor types. We got type 1, type 2. The major thing to take away from this guy is that you've got the bare metal hypervisors, which basically they use a bootloader to boot and get your hypervisor into and running on the actual silicone itself, and then they boot a management OS on top of that. And then you have the other approach, which is the Type 2 hypervisor, which is actually, it boots, think VMware Workstation, for example, it boots a general OS, and then you can fire up a hypervisor on top of that general OS.
So something that's sort of interesting to go into about the differences between these two systems is that's sort of what you're shopping for when you're shopping for a cloud platform. They just label it cloud. You aren't really sure necessarily what type of virtualization they're going for, but actually on the hardware level, it seems to matter a lot. Some of the power virtualization systems, for example, we know of attacks that took advantage of the fact that it wasn't actually running on the hardware or was actually running on the hardware. So just to correct myself, for this attack that actually ran on the hardware, one attack was actually dropping down to real mode, and in real mode actually calling interrupt vector table entries. And that totally bypassed the software OS-based patches, and this caused all sorts of problems for the host-based system, and multiple hypervisors have actually crashed from this particular issue.
So actually attacking the host infrastructure from the CPU itself, the virtualized CPU.
The other thing I should probably go into here, I think we'll get into it later anyway, but once you start working with the hypervisor in this way where you have to have virtualized hardware, you have to have communications to the virtual machine monitor, you're essentially opening up another interface that's expanding the sort of the threat profile of what this system actually is presenting. So normally you would say, well, I've got these services running, I'm running a patched kernel, I'm running all of this stuff, and that's generally your security posture, and everything's fine. But in this case, you really do have another kernel, and if you actually look at how this stuff gets implemented in these systems, they really do make these calls as though they were making kernel calls. They load EAX, EBX, ECX, EDX, and instead of calling int80, they actually do an I/O port call, which is a privileged instruction which the hypervisor catches and then services it as though it were an actual kernel request. The problem with this is that we've seen this go wrong under Linux, and we've seen this go wrong under Windows, and people seem to pretend that this back-end part of the systems on some of these, the actual power virtualization versus hardware virtualization, that part doesn't exist.
Patch right here. Yeah.
Yeah.
So you've got the two types. You have full versus para virtualization, and the para virtualization is when you're actually running. If you remember, you download and install the VMware tools on the guest. That's actually modifying the guest operating system itself to be able to communicate more intimately with the hypervisor. Versus via the Goldberg and Popick paper, you want to run. They recommend running an unmodified guest on the hypervisor. The problem with that is you have a huge performance impact because you don't have a marriage of the guest operating system closer to the bare metal. So that's the conundrum that we're in, is you have to sacrifice performance for security.
And when you end up running these, many of these patches, a good example is Parallels or Virtuoso or whatever OpenVZ-based hypervisors. For example, they actually require that the host operating system be patched, but under Windows, for example, you can't go in and patch the kernel. So what they do is they actually provide a device driver for every aspect of the system, and those device drivers abstract away what actually happens, BIOS call level, and just passes the intent over through the hypercall channel to the VMM. And the VMM itself actually performs that operation. And in doing so, it actually has to simulate a number of operations to look like the piece of hardware it's emulating. So if it's an ATAPI drive or a SATA drive, it actually has to simulate some of those SATA messages, some of those ATAPI messages to let the system know what's going on. And unfortunately, these very deep protocols we've seen in actual physical hardware have problems, and in many cases we've actually seen the systems themselves, reading, a good example is an ISO image format, that image format presents as a special disk, and that disk itself becomes an exploitable path for the system itself, and that's directly to the hypervisor.
Yeah. And just so you guys know, if you have any questions while we're going through this, feel free to raise your hands. And if we're going off in some area you don't really care about, just let us know.
I rant. I don't really let anyone talk.
Yeah. So here's the basic x86 architecture. Nothing new, but the crown jewels here are the MCH and the CPU, busting from ring 3 down to ring 0 at this level. And then if you can get control over the memory controller hub, then you pretty much have root on the system. So these are, if you're going to go after these machines or you're thinking about building a system, make sure that you're keeping these two pieces of architecture closely in mind for what kind of design decisions you're making on the hypervisor.
Is anybody actually familiar what the MCH hub is, what it actually does in the system? You're just too easy.
It is the Achilles heel of the system.
So in a lot of these modern systems, something that really isn't, I suppose, revealed to most people is that the memory controller hub in its own right is its own system, runs its own operating system, and actually has DMA view to the entire rest of the system. That embedded system itself actually has a number of sort of presented vulnerabilities since they talk directly to network cards and things like that as well. And these start becoming threats to your hypervisor.
Yeah. And here's our here's a fun one. So Intel wanted to have, when they rolled out the x86 architecture, this is what they wanted to have happen as far as the way that the developers broke out their applications. But in reality, what got implemented was this view on the left-hand side. So you can see where they've made the conscious choices going like, okay, we should really break drivers out away from the kernel just from a stability standpoint, security standpoint, et cetera. And the developers are like, well, that's great, but we're just going to do this. We're going to put the OS and the drivers right in the same ring, which has some security implications, of course. But they did that for backwards compatibility issues, and just I'm sure if I talked to somebody that was back doing this in the day, they'd have some better reasons about why to do that. But
actually, I looked into that a little bit. One of the reasons they decided to implement it that way was essentially whenever you want to pass one of those trust boundaries, that costs you some amount of a performance hit. So they just wanted to remove anything that wasn't a direct user space kernel transition, and everything else just kind of gets lost.
And of course, the little artifact here is IBM OS2 decided to do all of this. So if you guys want to run a system with isolation, that would be the one to choose from right now.
No wonder it was so stable.
Yeah. So here we got the hypervisor rings. The thing to take away from here is we have, right here we have the privileged ring 0, and then we have a deprivileged ring 0. So this is our guest, and this is our host. But what they've done is they've gone ahead and given the guest ring 0. However, that's actually is missing the access to CR 0 through 3.
Yeah.
And so that actually is not exactly a true ring 0 on the guest, which gives you some more process isolation.
And this would again be a difference that differentiates what particular virtualization technology you're using. So if you're using an AMD V versus an Intel VT, they actually implement how the GDT, LDT, IDTs are handled. Under AMD, they actually use the nested page model, which is actually really efficient. Under the Intel model, they actually allow sort of a number of models, but they don't support a nested page. But each of those presents a different sort of potential attack profile, and we started seeing that with cache timing attacks to be able to either have pages mismapped into another page of the virtual machine or to just detect that another system is active.
So you can start to get an idea here that your attack surface is growing. It's very much at the silicon layer. And so it's going to be very useful to pick up some of the x86 programming guides and get familiar with this technology sooner rather than later.
This slide is actually one of my favorites here. Now, like I just recently tried to figure out and decipher what this slide actually meant. And then, diving into the documentation a bit more, you can actually see down the bottom they have this node DMA where the display adapter goes through. That's, I believe this is from an Intel document. Yep. So that's actually Intel recognizing that DMA is a problem. So, for example, a FireWire attack under this system, if your host-based system actually supported FireWire, that would be a potential threat to your hypervisors on a physical level. But that also means that things like network cards and other devices are. The problem here is that the no DMA is actually implemented on the MCH, which itself has the ability to talk to the host system and, again, becomes another target for vulnerabilities. We're also seeing places where network cards like, not network cards, but other external devices like the NVIDIA card is one that I use. You can map pages of memory back and forth between the device and actually define where it maps that back. And if there isn't something very good at protecting it, you can stomp all over some things.
So growth over generalization is basically a hardware-based firewall for the mapping and unmapping of memory pages. So it's a after-the-fact introduction.
And you can also see that sort of the primary method of handling virtualization here is through the VMM. It's actually, this is again through the memory controller hub. As a memory request comes in from the CPU, it hits the memory controller hub, which decides who actually owns that piece of memory, and that actually returns control to the VMM.
And the thing is, with virtual machines, everything's done through memory. So if you have 100 virtual machines on one host, just keep in mind that your network paths are actually their bits being flipped around in physical system memory. It's never hitting the wire. It can be accessed. If you can get access to the paging system and know where memory is being allocated, then you own the system. Here's a Legrand, which is now called TXT or text. This is their secure boot process. This is the idea to try to circumvent some of the blue pill level attacks by trying to enter into a known, trusted compute state. There's been a lot of thought put into this guy, and you can see it's pretty complicated. But the Invisible Things Labs folks went ahead and they pretty much, I don't know if they've taken most of their life force, it seems like, and they've systematically broken each Intel security mediation on the hardware front to show that, well, SNR doesn't always get called, and they can shim in there before SNR gets called. And it seems like this cat and mouse game with those guys, but they do a pretty good job at it.
Yeah. So this is, I think this is actually under currently Intel's TXT technology. Intel actually has a number of different virtualization pieces that go with it, and this is the TXT, and only available on select motherboards and chipsets.
Yeah, so when you're making your choice, you're like, okay, I'm going to build my secure cloud, you need to really dig in, because just because it says, it might not actually implement the entire hardware protection set that you could get from Intel. You have to marry the chipset with the actual processor that you're using. Yeah, in back.
Do you have anything similar graphic on Pacifica?
You know, we need to get into that. That will be the next version 2 of this, and we'll provide it. Yeah, I apologize for the AMD folks, but AMD has similar technologies. They actually came out with the secure virtual machine idea before Intel did. Okay, here's a hypervisor attack surface. It has a lot of attack surface, and so we're going to just briefly go over what that is from an attacker's perspective, because if you understand how the attacker thinks, then you can understand how to go about defending it. Here's a quick attack surface analysis. It's not overly accurate, but it kind of gives you the idea of where things sit. So ring 3 is where your guest operating system sits. Ring 0, your privileged states, where your hypervisor sits. And unfortunately, to a lesser extent, some of your management system. So you've got the remote to host. Everybody understands that. It's somebody on the internet attacking the actual guest system itself. So you're running an unpatched version of fill-in-the-blank web server. You're able to get a foothold onto the guest operating system. From there, you might be able to leverage down into the host operating system. Remote to guest, that would be remote to guest. Remote to host would be actually attacking. Sometimes these hypervisors come out and they're actually exposing DOM 0 or the server core or the ESX admin interface to the internet or to a local LAN segment. Never ever do that. These things, if you dig around in the CVE articles, they have nothing but massive unpatched attack surface. I mean, things like copying malicious fonts into X11 directories, taking out your hypervisor. I mean, it's no end to it. I actually lost count. There's so many vulns out there right now for the actual management piece of the hypervisor. So I think maybe like, one-way diodes talking to that, almost treat them like SCADA systems in a way. Like make sure you have a solid air gap between the management interface, the allocation, deallocation of virtual images. So it's a big deal. And then you've got a guest to host. You have a massive attack surface there. You have the guest can attack the tools interface, the VMI interface, the hypercall, hypercall, VMI, they're all kind of in the same bucket. So this is actually the guest operating system calling into the hypervisor through exposed APIs. And if you want to talk about the I/O backdoor, is that good?
We went through that. I think we covered that a little bit at this point, but that's mostly just the sort of secondary kernel interface that you would actually be passing these calls through on a lot of these.
There's a fun attack where people are trying to figure out how to patch the BIOS, and then from patching the BIOS, they create a malformed E820 memory map that gets fed back into the hypervisor and then owns your hypervisor. It's kind of a chicken and egg game, though. Like, if you've got that level of access, then why own the hypervisor? But it's like, really? So you can, from the bottom up, you can own the hypervisor, and from the guest down, you can own the hypervisor. Hypervisor, for the management interfaces, exposes a networking stack that can be compromised. So there's all these interesting angles that you have to keep in mind when you're going to deploy your private cloud.
And then there's some weirder things that also end up showing up, especially when you're talking more public cloud, I suppose, than private cloud. But the virtual system images themselves start becoming potentially hostile images, and CD-ROMs I've sort of already covered. One really interesting anecdote somebody had given me is actually suspending a system under an AMD device and restarting the system under an Intel device, and that actually crashed the hypervisor. And one of the reasons that some of this stuff seems to happen is that under some systems, and I'm just taking the shortcut out of this, right? So they may have SSE2, SSE3, and then they move to a new system that doesn't support these, and suddenly the VM thinks that these invalid instructions are on their way to being executed anyway, and that generally brings the system to a halt. And we keep seeing these other surfaces now that get exposed, like the web interface. Amazon's EC2 is a really interesting one. If you've got your whole corporation sort of integrated into that, like one good cross-site scripting bug.
And Amazon has a two-factor token, as probably sure everybody's seen, so definitely highly recommend grabbing that guy. You can buy it right off the website. So those are some things to keep in mind. People are, there's like an integer underflow in the E1000 driver that you probably like, if you think about that when you're like, so there's an integer underflow in a networking driver. Oh, that networking driver gets virtualized. So now you've got your guest operating system that you've spun up on somebody's massive cloud infrastructure, and you literally have a virtual interface that has a buffer overflow or underflow or whatnot that you can attack to get into the hypervisor. So we're talking like if you want to look at the number of inputs into the hypervisor, it starts to like boggle the mind, or at least mine.
Actually, since you covered the E1000, another sort of side effect of the E1000, you can look this one up. It's actually a really fun vulnerability. You can actually feed the E1000 various MTU sizes and get the E1000 to sort of say, that's not a valid message, I have to fix it. But it only fixes it enough to pass it to the host system, and then it just sort of gives up on it. Some really clever people have figured out that essentially they can send it a sort of large MTU packet with a normal packet that would normally be rejected by the system's firewall in the first part. But the way that it actually reformats the packet is by splitting it and allowing a new header to actually be formed, and that becomes a new packet that has already passed the check. It is now already inside the network, and at least one way you can potentially talk to other hosts. It wouldn't be a bidirectional communications thing, but that was a really clever issue with the network card.
Complexity is definitely the enemy of security. This is probably way too small to look at, but we'll go over a couple of these bugs.
I can't read it.
So in 2006, it's kind of when we first started seeing some attacks against hypervisors, virtualized rootkits. In 2007, we saw the Xbox hypervisor exploit come out, which was a big deal. They had to like do some serious engineering on that to fix that bug, basically risking the games from being pirated and whatnot because the hypervisor got exploited. Virtual PC had a buffer overflow on it, a heap overflow in the VMware VM system. And so we kind of see this. This is just 0.005% of the known vulnerabilities right now against hypervisors. So don't think when people are like, well, I've never really seen a valid attack against a hypervisor, you have to read closer. Yeah. Because what they're saying is they really don't say like the hypervisor got attacked, they're like the host system got attacked. The host system has the hypervisor, and if you look really close, you'll see you've got root access with some of these vulnerabilities. You've got the Flask remote buffer overflow on Zen. So NSA took the time to write a security module for Zen, and it had a buffer overflow in it. It was remote code execution. You had this is not a good day for anybody, I think. There was through Server Core, no fault of their own, but they had a Server Core as the Hyper-V system technology. You had a remote RPC buffer overflow in it. So if you forgot to lock off the management interface for your Hyper-V installation, you just got owned over an RPC attack, and therefore your hypervisor altogether. It's a bad day for everybody. And then there's a new one. We haven't. On the virtual 8088 mode, you can actually, if you're a guest in the cloud system, you can flip the CPU.
So I tried covering this a little bit before, where they essentially dropped into real mode and then tried calling interrupt table entries directly and bypassing the VMM patches on the OS.
So actually using the chip itself, the mode that the x86 processor is in, the virtualized chip, and attacking the host system.
Well, interestingly, if anybody's written a fuzzer for things like the VMware backdoor and things like that, try again in real mode.
Right. Yeah.
Some of these messages actually can't be executed from anywhere else but real mode, and different things actually happen based on, where you've actually done these things. So either in real mode or actually from kernel space, interesting things happen.
Yeah. So we got some really heavily technical attacks at a very low level. One of the interesting things here is Q35 attack. So you've got the no DMA feature. This actually required a binary patch to the motherboard to fix the Q35 bug. It basically, the BIOS wasn't written in a way that actually extended the feature set on the Q35 to do DMA blocking. And so if you had a huge cloud deployment and you're like, okay, well, we've got no DMA turned on, excellent for us. You find out later that the BIOS calls weren't set up right to block the DMA calls. So then you're looking at the data center going, we have to do what, patch motherboards? And that would be correct. The answer would be yes. So that's yeah, that'd be a lot of work, I guess.
I think we're starting to get close on time.
Yeah, so we'll keep going here. Did you talk about the IO? We wrote a fuzzer for the backdoor feature in VMware. So if anybody wants to download that, it's on our website. You can play with it. This basically this privileged IO call.
Again, I highly recommend real mode.
Yeah, you can grep through some of the VMware stuff. And you can see there's a ton of features exposed in the backdoor system that VMware has. So here's great. So like perfect. We're in a world, again, where we've got a lot very complex technology. How do we go about securing it? You know, a lot of doomsday type of rubbish, but there are, you know, definitely good things that are happening. Intel's made the investment, AMD's made the investment, so the idea would be make sure you do your research into your hardware selection. I mean, it really is. Like, make sure you get the right hardware.
The right hardware, the right hypervisor.
Yeah, the right hardware married to the right hypervisor. There's lots of different hypervisors out there that you can choose from. IBM has vHype. There's Box. There's Cubes out of the Invisible Things Labs that you can take a look at. That's more of an architectural approach. There's something out of General Dynamics called HAP. HAP, take a look at that. But test all this stuff at the end of the day. Don't just grab it and go, I'm secure. It really seems like if you can get away with it, disable that patch modifying the guest operating system, play with the hypervisor. There's so many attack vectors from that one modification of the guest operating system. It's not ready for production, if you ask me. And then, of course, dedicated physical interface to your management of your HVs. And then the other fun one is probably, I'm sure everybody in this room has thought about it, but if you virtualize your entire network, so you've got guests talking to the guests over a map, memory region, et cetera, how do you detect whether or not there's any kind of nonsense going on there, any kind of covert channel? So you got to figure out how to trap that network traffic, to analyze it, to see if there's any kind of compromise. So a lot of people are now like breaking out, they're pushing the network traffic out over physical interfaces and then back into the machine so they can actually monitor it. So anyways. All right, well, thanks for listening, guys. Hopefully we didn't bore you too much.
Are you talking about you know, some of these devices like I'm thinking Sidewinder that has a number of virtualized sort of systems inside? I haven't looked at any sort of applications directly. Most of my work has been sort of directly on the hypervisor and trying to either break out or trying to disrupt a neighboring VM. I'm not really sure entirely what they use. They could be using something more along the lines of what BSD uses, where they keep an entire operating system in this sort of virtual image, but it's not an entire kernel. It's not an entire system. I'm not entirely sure.
All right, back.
Did you quite catch what the real issue was with virtualizing the entire network layer?
So right now, the organization has a host of systems that they use, like IDS, IPS, you know, bump in the wire style systems, MRTG graphs, for example. And when you put 100 machines onto one blade, for example, you lose the ability to see that network traffic because it's all running within the context of that server environment. Yeah, I mean, it's a really basic one, but you know, it's. Yeah, you could fire up. I mean, you can do things at the virtualization at the network layer to like pop that data out to get it analyzed, but you need to make that active step. Right. Yeah, you got it.
Which some companies would love, is that costs you extra money to run that extra VM, and then I mean that's sort of the architectural problem, is you end up having to solve a VM problem with more VMs.
Right. All right. Thanks, guys.